perpendicular to the mirror. So this is the perpendicular that you care about, and this is the 35-degree angle. Okay, so there's a reflected ray. That's the reflected one. And then the incidence ray, which I don't know what it is, but this is the incidence ray. And they want the angle between these two. Is that okay so far? So
Yeah.
for sure, we know that this is 35 degrees. And then because these are the same, because the way it comes in, way it goes out, and then we can get this by 90 minus 35. So that's 55 degrees. And then the question is, well, what is this angle over here? I'm sorry, this is the incidence ray. Forgive me. I don't know why. This is the refracted one down here. Misspoke completely. Sorry. Just these words are, I don't use them all the time. Incidence is the one coming in. Reflected ray is the one going out. So actually, this is fine over. They actually want this angle right here. It's just double the 35, which is 70. So they actually want this one there. Hopefully that is clear. All right. Next question here. Sorry, get my snipping tool to be in the right spot. Here we go. All right. So next question, kind of the same deal here. It's asking you got a light ray coming in that's 0 degrees to the perpendicular, basically. And like, I think it's confusing because you really want it to be from the surface, but in this case, it's from the perpendicular. So it's 0 degrees. So it's like it comes straight in, bounces straight out, and the angle of reflection is the one that goes out. The angle of incidence is the one that goes in. They're always with respect to the perpendicular. So it's the same angle. Same angle in, same angle out. Okay, next question. The figure below shows how the word ambulance is painted on the front of some vehicles. Okay, and the idea is that when you look behind, and so this is on the car behind you on their hood, which is awkward because I think you said you're driving. If you look at a car, like your car, whatever make and model it is, it's not written in reverse. Like if it's a Ford or Chevy or Toyota or any of the brands out there, right? Like it's not written in reverse. But when you look in your rear view mirror, this actually like when you look in your rear view mirror, you got your mirror and your rear view mirror here, you see it as ambulance. Okay. So why does it do that? Makes the objects appear farther away? No. Rotates the objects by 90 degrees. So if it were to rotate this by 90 degrees, it would rotate like that. So that's a no. Turns the word upside down. That would flip it. So I guess it's this. Although that doesn't really read right to me, but that's probably the best answer.
Okay.
All right. So next question here. So you're moving into this part of the course where when you look into mirrors, depending on the style of mirror, you have both real and virtual images and upside down and not upside down. And it depends on whether the mirror is this type of mirror or whether it's this type of mirror. And like I'm sure you've been to malls and looked in the mirrors, and full disclosure that some of them use mirrors that tend to make you scale differently. And if you ever went to like a funny house circus thing, they go to the extreme, but this is going on. I mean, it's no different than a filter on Instagram. You just like, this is what happens. Now, in terms of the answer here, I need to look up what a concave mirror does. If you stand Okay, so the concave mirror is so it's like you're here, and this is the mirror, and like the focal length is here or something. So you're just closer to it. This is just a pure definition. It's virtual and upright. So there's some equation you can use, but we'll just go with that for the moment here. So by the way, this is all useful in astronomy, trying to and August is a really good month for astronomy. I was reading an article. If you're into that, there's a lot of stuff going on right now that you can't see very often. Okay, which one of the following is not a property of images formed in a plane mirror? Plane mirror. Okay. Okay, so I got to kind of look up properties of plane mirrors. It says it's laterally inverted. So this is the one that you're used to seeing when you look in the mirror in the morning. Same with me. The first is that, so these are true. It is a virtual image. Okay. It's the same distance, but like you appear to be the same distance in front of as you are behind it. Okay. And then the question is whether the images are enlarged. And the answer is no, they're not enlarged, but they are sort of reversed left and right. They sometimes call that laterally inverted. Because it's the same size, like you don't look bigger or smaller. So this would be the best choice, in my opinion, with this. Okay. Next question. So a ball is held 50 centimeters in front of a plane mirror. So here's the ball, and this is 50 centimeters. Okay. And we just talked about that. It appears 50 centimeters virtually behind the mirror. And so the distance between them, the total distance is 50 plus 50, 100 centimeters. And I think the confusing thing is, like, you feel like it's like on the mirror, but it's actually like behind it, but not, it's not real. That's why they call it virtual.
Mhm.
Yeah. So let's see here. How many emails did you? Okay, so we do have a bunch more to go through. All right, let's try to get through a little bit more of this. Oops, not that one. Okay. When an electromagnetic wave meets a smooth reflecting surface, the direction taken by the reflected wave is determined by. Like this is again, like it's coming in, but it's some sort of wave, and then it's going out, some sort of wave, and the direction here. Since it's not going through, we know it's not the index of that medium because it's reflected. If it would go through, that would be the refracted. The rest of it, okay, probably not the intensity of the wave. It's probably the material, the angle, or the wavelength, but probably not the wavelength because it's a property of the wave itself. So I think this is just a definition. So I'm going to keep looking up a resource for this. I don't know. So it's strictly the angle of incidence.
Okay.
Angle in, angle out, I guess. I mean, that seems very simple, trivial, but I don't have any other thing here. Okay, so next question here, we got a dog standing in front of a mirror. It doesn't have to be a dog, it could be anything. We know that the image is not real. We know it's not inverted. We know it's not reduced. We know that it's the same behind the mirror as it is in front of the mirror. And so they're really driving home this like property of things here. All right, so here's the next question. We saw this question, let me slip it in. We saw it in a different context. This one, let me grab it here. So we saw this question before where it was actually like water waves coming through. Here it's like something coming out and then it goes through, it bends around. And whenever whenever there's something sort of bending in this case, that is diffraction.
Okay.
We can safely assume that none of the other options make sense. Okay.
Okay.
Next one here. So the law of reflection is that the angle of incidence equals the angle of reflection. So the angle in, that's the incidence, equals the angle out. Incidence equals reflection. Okay, so light reflecting from a smooth surface. So light comes in, light goes out. And what I don't know here is again, like which of these properties, if any, change. I think it has to do with this fact that it's like a smooth surface that probably, like, to someone that really knows this stuff, they say, oh, well, that's clearly this. But let me just look So based on like our earlier discussions, we just said it just bounces. It doesn't do anything. So I'm going to suggest we go with none of these. And that's probably because of this smooth surface. Like if it wasn't a smooth surface, maybe it does bend around and does something different on the way out. But that is my best guess based on that. Okay, so now I know you sent some more emails. Let me go back and grab the next couple here. So I assume there's not a particular order that you need this done in.
Oh no, the order doesn't matter.
Okay, okay, because it's all right. So here is. All right, so two waves traveling toward each other in the same medium. Left, it's +1. So they're saying, hey, that's a height of 1. That's a height of -3. And it's like, what happens when they overlap? I think is the question here. They go grab that. And they're saying like, well, which one is it when it overlaps? So the positive, the +1 and the -3, they cancel out to, you just sit there and add to -2. So it's something that's going to have a height of -2. Okay, and I think you can see that that's letter D in the diagram there. If they were exactly the opposite amplitude, then they would cancel out completely. Okay, we actually just answered this question here. Let me grab it. Yeah, there's like 4 things you got to know. You got to know incidence, that's the one coming in, reflected going out. Refraction is when it goes through a medium, and then diffraction is when it bends around the edge of a barrier. And that's when we saw with the kind of the water waves and then the light again. So, you know, like that's kind of the main takeaway. Like, you know, we're just moving through this pretty quickly, but that is, that would be a good thing to kind of take away from this course right now. Is like, what are each of these things actually doing? So here we go. Which set of wave characteristics belong together? This is a great question that I'm not sure of. Let me just check here. This is one of those where it's probably in multiple sections of your textbook, because it's like combining them, or there's a summary. So the mechanical waves is kind of what I'm leaning towards, of like which ones to discuss first, because mechanical have different properties, either longitudinal or transverse, things like that.
Okay.
But let me see if I can find an option here. So option C. So I'm sorry, not option C. The electromechanical, where, and we didn't talk that much about them, but they do not require a medium at all. I mean, that's why we can move. That's why we can do wireless and Bluetooth and other things, because the waves just move through the air. And light waves are more like these than that. So sorry, not a great explanation, but we'll just keep moving on here. All right, next question talks about constructive interference. So interference is the word we use when it's either constructive or destructive. So constructive is positive. It's like two things combining together. So when two sounds. Okay, sorry, these are weird questions. So two ocean waves passing through each other, but they decrease in height. That's not constructive. That would be destructive. Two sound waves overlapping and getting softer. If they got louder, that would be constructive. So that's destructive.
Mhm.
Two beams again getting dimmer is destructive. We're looking for something that adds together. So again, these are all examples of destructive interference. Okay, let me grab the next question. Okay, if the speed of the wave changed as it entered a new medium, which direction is the most likely path taken by the wave? So notice like it's like saying, hey, it went straight here. Here's where it started. And if it were the same speed, it would go like that. Like if it just perfectly passed through without like any changes. Okay.
Mhm.
So that leaves 2 and 4. And in one case, it's probably changed its speed faster and slower. Not sure which one though. And it doesn't really matter because I think we're just choosing, but it looks like 2 or 4 is an option. The one that's just
Mhm.
perfect. I mean, that's almost like there was no barrier, but 2 got redirected and 4 got redirected.
Mhm.
Now, actually, kind of, I don't know. You swim a lot, like you got the different lanes. Like, do you ever notice the water impacting you? You know, one lane to the next.
Like how it feels.
Yeah, like, can you notice that when someone's breaking up the water? You know, either in front of you or behind you or anything like that.
Oh yeah, yeah.
Okay, and that's kind of what's going on here. Like, think of this. Sorry, my screen is frozen. Please unfreeze. So this would be like your medium that's that I don't know what it's called. It's the rope thing between the lanes, and their waves are traveling at you, kind of thing. So okay, new question here. If the speed of the wave, I think we already answered this, but if the speed of the wave changes entering a medium, that is refraction. I'm sorry, diffraction. No. It's I'm sorry, it is diffraction whenever it bends. So there's kind of another question here on with the same image. This time it's asking about reflection. Let me snip that in. So it says reflected wave. So here's the start. There's the reflection. There's only one. In, incidence, out, reflected. So it's obviously option 1.
Mhm.
All right, so on to a new email here. Lowest frequency. Okay, so here's a definition. Frequency is 1 divided by the period.
Mhm.
Okay, so the smallest frequency corresponds to the highest period. It's a weird relationship, like 1 over a large number equals a small number. Like one, like and sometimes you gotta think of like, well, what's 1 over 10 compared to 1 over 100? Well, 1 over 100 is smaller than 1 over 10. So since it's a smaller number, or since this number is larger, that's the smaller frequency. So we're looking for the largest period. Okay. And so period is peak to peak. So this one looks like it has the largest period. This distance here. There is another way to look at frequency, which is like the number of cycles that pass through it. Like if you were to just stand there and watch something, like you could think of it as like cars passing. Like this last one's a really slow car passing in front of you, whereas this one above it's a really fast bunch of cars going in front of you. So that would be our best choice there for that.
Okay.
The source of nearly all wave motion is, interesting. I don't know. I would say vibration, but this feels just, one of those, it's like, well, that's like so obvious that maybe there's something else here that I'm not seeing. So let me check here. So a harmonic object is motion. So I guess I would go with this one. That would be my best guess on this.
Okay.
Wish I had a better explanation. Okay. Next one says to use the diagram below to determine the amplitude of the wave. So the amplitude is the distance from the center line to the peak, or the distance from the center line to the valley. Since they're giving you the top to the bottom, you just cut it in half, and that's your amplitude. Yeah.
Okay.
So next we have a question on frequency of a spring wave. Frequency of a spring wave. As the frequency of a spring wave increases, so frequency is going up. So what we need is something that has to do with wavelength, or probably not velocity. So the length of the wave is like this, which I think of as period. So remember we had two pictures. We have like, this would be a really long wave and this would be a really short wave.
Mm-hmm.
So 1 over the period, 1 over the wavelength, you can think of. So the one with the shorter wavelength is going to have a higher frequency. So this seems to make the most sense to me. Let me just double check that. I know that it's important to get it right. Yeah, we got it. Okay, great. So we kind of already answered this question here, looking at question that says all of the waves listed below except blank must travel through a medium. Believe that light does not travel through a medium. That was that kind of related to that electromechanical question. Because it exists where there is no medium. Yeah. So it is definitely light. All right. Sorry, I need to just step away for like 2 minutes. I'll make sure we get through this. Just let me step away. I'll be right back. Okay, Julia, I'm back. We're on this question about characteristics of a mechanical wave, which I will snip in. Which of the following is not a characteristic of mechanical waves? So let's go with the things that are kind of like should be kind of obvious about mechanical things. Mechanical waves, they do have energy. They transport energy. They're definitely created by a vibrating source. Okay. And then they consist of disturbances or oscillations of media. Absolutely. So therefore, it must be this first one. They always travel in directions parallel to the direction of motion. I guess they could also travel perpendicular to them as well. So go with that one. Okay, we got another question here. It says true or false. These are always fun. So in order for sound from a speaker to reach a listener, air near the speaker must travel to the listener. Boy, what do you think when you read that? Because then try to just be intuitive about it. Like imagine your phone, to hear something from your phone, like air had to rush to your ear.
Oh, I don't know.
Well, it seems really odd, right? But I just want to double check because like to me it's like, you're watching TV, you don't have like air coming at you. But what it could be is that it's moving so small, and that's why I'm like want to check this, like whether it's true or not, because it's just a weird. Yeah, so this is definitely false. Okay, it's like an intuitive thing that we have here. Okay, so let's see here. Ooh. Have we gone through all the questions that you sent? It looks to me like we may have.
I think so.
Is there some more that you would like us to answer? Oh, no. I think there's one more email here. I'm sorry. Yeah, sorry, I didn't catch this. Okay, so here, the question is asking, it gives a nice picture of a wave. This is ideal to start when you're learning this subject. So it says it's only moving kind of parallel to the direction. Like it's moving to the right and to the left. Okay, and that is a transverse wave. The longitudinals are the ones that move perpendicular.
Mhm.
So the next question actually is really similar because it's showing a diagram where you pull, snip this in here, you pull the spring, like you pulled it out away from the wall and then you release it towards the wall. It just moves back and forth, back and forth, back and forth, back and forth. And that is transverse.
Mhm.
Just let me just really quickly oh boy. I feel like I might have just got this wrong. No, I'm so sorry. I mixed these up. So longitudinal, this is so bad. So longitudinal is when it's going back and forth. So this one is actually longitudinal.
Mhm.
Transverse is when it's going counter to the direction. So that changes the previous one as well. This previous one is longitudinal.
Okay.
And glad I caught that because it. Okay. Let's see here. So the next question. Which wave has the largest amplitude? So we're just looking for the biggest difference from the max to the min. We could cut it in half. Basically, it's the tallest wave. That looks like A. A is the largest because it's got the biggest top to bottom, or you can cut in half.
Mhm.
Okay, shortest wavelength. So we can answer that. That's literally the length of the wave, and it's the same 3 ones. So we're looking for the one that kind of like stretches out the most. I'm sorry, stretches out the least because they want the shortest. Shortest wavelength. So these are this one is much shorter because it only takes one box to complete a full wave. And
Mhm.
like the C takes 3.5 boxes to make a full wave, and A, down, up, down, it takes again 3.5 boxes to make a full wave. So the shortest wavelength takes the fewest boxes to make a full wave.
Okay.
Waves transport. So they definitely transport energy. Like when I think of waves in the ocean transporting matter, I think of things like moving up, riding them. But let me just check here because we want to get this right. So waves transport energy. No, just energy, just energy. So matter is something totally different. It's probably emphasized in a lecture, but all right. Okay, I think, no, maybe not the last one. So a wave which the particles vibrate up or down or perpendicular to the direction of travel for the wave is called, and that's the one that we like the ocean wave, but the ocean actually moves both directions. I mean, that's not a good example. Let's see here, check. So it's definitely a transverse wave. The question is it a mechanical wave? And it would be, so I think the direction of travel for the wave. So I think it's just a transverse wave because that's the one we're talking about. The energy is moving up or down relative to the wave's motion, which is that way. A longitudinal wave would they would talk about somehow moving forward. So that's why it does not turn into all of these. And I think that's it. Is there anything else you want to send over?
That's
Do
it.
you want to scan? You think so? Okay. All right. Well, I hope that works out. We've got a new schedule for SAT prep, so I'll send that over as well. And thank you so much for letting me help you, and I'll see you next time.
Yeah, thank you so much.
Bye-bye.